Okay, good morning to all of you. In the last class, we have talked about the classless interdomain routing and how IP address is provided into different interfaces of a router, and then how IP address is used for the routing purpose. That means whenever you are receiving a new packet, then how you are going to find out the routes. So today, starting it from that point, and we'll also look into that how you can generate or how you can design the routing tables, or how the internet actually forms the routing table when different machines are interconnected. So to start with, here is just a sample problem for you. Kind of practice problem or a part of it we are going to solve. So this is a part of the routing table that is being shown. In the routing table, we have the three important columns. I have not put up the columns corresponds to the gateway here. Just put the next hop. So the IP is given. That IP corresponds to the network IP. Then we have the net mask, and finally we have the corresponding next hop interface. Now, in the right-hand side, three different IP addresses have been given. So these IP addresses are corresponding to the destination IPs that are being received from a packet. So, for example, whenever you are receiving a packet and the destination IP is 128.96.171.92, then you have to find out that what should be the next hop based on this routing table. So the procedure we have discussed earlier, that the general procedure is that you take this IP address 128.96.171.92, do a logical and with the corresponding net mask, and see whether you are obtaining this network IP or not. If you are obtaining this network IP, that basically means that this particular IP address 128.96.171.92 is a part of this network, and the corresponding next hop is going to be your next hop. So let us take our first IP, 128.96.171.92. So if I just convert it to the binary and do a logical AND, and we will get it is coming to be 128.96.170.0. Okay, so we are just showing here this third octet, because the first two octet you can see it is 255.255. So if you are just doing a logical AND, it will be coming to 128.96. Then the third octet is 171. 171 is logical, 171 binary notation, it is 10101011. And if I take net mask as 254, then if I 254 equal to 11111110, if I do a logical AND, I will get 10101010, that is 170. So my destination is going to be 88.0. Okay, so that is the standard procedure. But there is one catch which will not be true for this particular case, as I was mentioning in the last class, that there can be multiple matches simultaneously. Okay, so that's why you should also do a checking with other IP net mask combination. So if I take the second one is also 254. So there is not a match. If I take the third one, again there is not a match. The fourth one, if you do a 252, you will see there is not a match. The last one, that is the default route, there is a match, but we will also always take the longest prefix match. So we will take the first one. Well, and the next hop will be 88.0. Okay. Now for the next IP address, 128.196.167.151, for this one, if you do a logical AND with 254, for the third octet 167, you will get 166. So we see that there is a match here in the third entry, 128.96.160.0. Okay. But again, for this particular one, if you take 252, then also you see it is coming to be 160, 252, so it will be 164. So there is a match in the fourth one as well. Okay, so we see that there is a match with the third one and the fourth one. So there are two matches. So in this case, as I was mentioning earlier, we'll take the longest prefix match, and the longest match here is in 254. So we take the next hop as the third one. Okay, it should not be TH1, it should be R2. That's a mistake here, it should be R2. So we had a match with the third one, where the next hop is R2, with a match with 128.96.166.0, and a match with the fourth one. Okay. But the longest prefix match is coming to the third one, so we'll take the third one as the intended next hop. So my next hop will be R2. Okay. Any doubt up to this point? Okay. So this is the general procedure to find out the next hop for a given IP address that is coming to be as a destination IP in a packet. Now, the important question that we have, that till all this discussion, the yesterday's discussion, the last class discussion, and the discussion till today, we assume that somehow this routing table is known to a router. Okay. So whenever the routing table is known to a router, what you do that you take the incoming packet, you get the destination IP, make a match with the routing table, find out what is going to be your next hop from the routing table entry. Well, but the question is that who is going to provide this routing table to the router? Well, or how the router is going to generate this routing table. Well, so that is the kind of important and interesting question. So now we are going to look into that aspect of the routing. So where we see that how the routing table is being constructed. So from this particular aspect, later on we'll discuss these aspects in details, that typically in a router we have two different important functionality. One functionality is that for every incoming packet, you extract the destination IP, then from the destination IP, given your routing table, you make a routing match, find out what is going to be your next hop, and forward that packet to the next hop. Right? So that is one task of the router. The second task of the router is to construct that routing table. Right? Because once the routing table is given, you can do the remaining tasks. But how you are going to form that routing table? Now to form this routing table, every router runs some protocol which we call as the routing protocols. Right? Now in internet, we have two different variants of routing protocol. One is called the intra-autonomous system routing protocol or intra-AS routing protocol. And the second one is called the inter-AS routing protocol. Right? So you remember, I hope, that the definition of an autonomous system. So autonomous system is basically a subnet which is managed by a single administrator. The example that I have given you, that our IIT Kharagpur network is an autonomous system which is being managed by our CIC. Now, typically, these routing decisions within an autonomous system is decided by the network managers of that particular autonomous system. Right? Now, what is intra-AS routing protocol, or sometimes we call it as the intra-domain routing protocol? So, this intra-AS or intra-domain routing protocols are the routing protocols which run within an autonomous system. Okay. So the purpose of this intra-domain routing protocol or intra-AS routing protocol is to forward a packet within an autonomous system. Right. The example of such kind of routing information protocol or RIP, then open shortest path first or OSPF. Well, so sometimes these kind of protocols are also called as the interior gateway protocol or IGP. There is another class of routing protocols which is called the inter-AS routing protocol, or sometimes we call it as the inter-domain routing protocol. So these inter-domain routing protocols, these are the routing protocol which forward packets from one autonomous system to another autonomous system. Right? So based on the peering relationship among the autonomous systems, so it basically dictates that how individual autonomous systems are connected, and then accordingly decides that how to forward the packet from one autonomous system to another autonomous system. And the example of such protocol are the border gateway protocol or BGP. So this kind of protocols are also known as exterior gateway protocol or IGP. Now let me explain it with the help of one example. So yeah, so this is the kind of broad idea of how we are going to forward the packets, or rather, let me explain it in a clear way. So typically, whenever you are forwarding the packet, if you remember our internet architecture, so it was something like that multiple autonomous systems are interconnected. Okay, and those set of autonomous systems, we call them as the internet service providers, or a group of autonomous systems we formed a internet works like an internet service provider. And then these internet service providers are providing internet connectivity to the end users. Now, whenever you are forwarding the packet, there are two things. One is like, based on the IP address, you need to decide that how the packets are being forwarded within an autonomous system. And then the next thing is that how packets are being forwarded from one autonomous system to the next autonomous system. Well, so based on that, actually, we have these two classes of routing protocols. So as we proceed and as we discuss further with the design of such routing protocols, the things will get much more clearer to you, I guess. So this entire routing in the internet that is based on one algorithmic foundation, which is called the optimality principle by Bellman. Okay, so in a graph theory, you have already learned about the shortest path algorithms in a graph, like the Bellman-Ford algorithm. That was also based on such kind of optimality principle, which basically says that if a router is on the optimal path between two other routers, then that particular router also belongs to that optimal path. So, for example, if this router J is in the optimal path from router I to router K, then I to J is the optimal path and J to K is also the optimal path. Okay, so that means subset of an optimal path is an optimal path. So the internet routing basically works based on this principle, and based on this principle, what we try to form for this routing is something called a sync tree. Now, what is a sync tree? A sync tree is something like this. So this, I think sometime back I was mentioning this to you, that internet, the entire internet, you can imagine it in the form of a graph. Okay, so where every entity, like every individual nodes, like a router, end host, you can assume them as the kind of node of that graph, and the link between them is considered as the edge of the graph. Okay, so here in figure A, we have shown an example of such kind of network graph. Now, what is a sync tree? A sync tree is basically the set of optimal routes from all sources to a given destination. Okay. Now, if I construct the optimal route from all the sources to a given destination, they form a tree kind of architecture rooted at the destination. Okay. So, such a tree is called a sync tree. Right? Because all the packets are reaching to that particular node. So here, for example, this.
Sir, your presentation is stuck.
Can you please repeat?
Sir, your presentation is stuck, I think.
The presentation is not coming?
No, it is stuck. It was stuck on slide 2.
Oh, it is stuck on slide 2. Let me close it and share it again. Can you see it right now? The slide corresponds to symmetry.
Yes, sir. Yes, sir.
Okay, good. So yeah, so here is the example that I was mentioning that in case of a symmetry, so what we basically construct that all the optimal paths towards a particular destination. Okay, so here in the example that say B is my destination. So while we decide about the routing of a packet, we try to construct the symmetry destined at node B. Right? So here from all other nodes in the internet, I will find out the optimal path towards node B. Okay. Now, here is an interesting question. Right? So why do we do like this? So why we are more focused towards a destination-centric tree rather than a source-centric tree? So I could have constructed it in the other way, right? I could have constructed it in the form like I would consider every source in the internet as the root of the tree and then find out the paths towards that source. But we do not do that. Right? Rather, we do find out the paths, all the paths towards a particular destination. Okay. Any idea why we are doing it like this? Just think about what is our objective of forwarding the packets, or what issue or what optimality challenge we might have if we try to construct a source tree for internet routing rather than a symmetry. Any idea? Just whatever is coming to your mind.
Sir, while forwarding the packets, the router will move the packets more closer towards the destination only, right? So if you form the source tree, then like you will not have that information like whom to send to. Means what is the path that we need to send to? Because the source tree will have no meaning, because the source tree will mean that we are expecting the packet to come from that path. And
Okay.
the destination will not know that packet needs to come from that source only.
Okay. Good. So yeah. So whenever we are doing the internet forwarding in the internet, what is actually happening? So as you are mentioning that for every router, my purpose would be to forward the packet to the next hop towards destination. Okay. Now that way, if I just try to imagine that how the things get forwarded recursively, it is something like that. I start from the source, go to the next hop. From there, I will again try to find out that what is going to be my optimal path towards the destination. I forward it one hop further, and that way I will gradually move closer to the destination. Okay, so that means the decision that I have to take at every router is like how to forward the packet closer towards the destination. Okay, and that is the reason we make more focus towards destination centric. We could have done it using a source centric tree. If you think of, you can design an algorithm or design a mechanism for that. But you will find out that that kind of architecture is much more difficult to implement in case of our internet. Because remember that whenever you are going to learn this shortest path algorithm in your graph theory or in your algorithm course, the entire network graph is given to you. Okay, so you have the graph, you need to find out the shortest path between two nodes. But in case of internet, the challenge is that the graph is not there. Well, because every node do not know what is the entire internet graph or what is my entire internet graph. Okay. So because I do not know what is my entire internet graph, that's why the challenge is that how to decide, or for every node, every intermediate router, how would I decide that what is going to be my next hop depending on my end-to-end path? Okay, so that means whenever I am going to use the same shortest path algorithm that you have learned in your algorithm course or a graph theory course and try to implement it from the perspective of a practical system, I need to do some tweaking in the standard algorithm. Actually, we'll see why we are going to discuss about the original algorithm or the exact algorithm. That we'll see that we do certain system level tweaking for doing such kind of implementation. Okay. And that tweaking are actually the interesting stuff and the kind of important stuff from the system perspective or the network perspective. So that way the algorithm differs a bit about whatever you are going to learn in your algorithm course and whenever you are going to implement it in practice. Okay, we'll see more such example of it. Okay, so can you see the next slide just to make sure?
Yes, sir.
Yes, sir.
Oh. So as I was mentioning, that seeing tree for a destination, and this is another important thing, that seeing tree for a destination may not be unique. Well, because there can be alternate paths between two routers with the same path. Well, and in internet you have seen that due to multi-homing we can have multiple paths towards a sink or towards a destination. Okay. So that's why typically we may use a more generic data structure like a directed acyclic graph or DAG. That denotes all possible paths from all sources to a destination. Well, so from the internet routing perspective, both a tree or a DAG is okay. Our only objective would be to ensure loop-free routing. Now we have actually two classes of routing protocols that we are going to discuss throughout this course. One is the distance vector routing, and one is the link state routing. Okay. So first we are going to learn about the distance vector routing, and then we are going to learn about the link state routing. Now, what is the distance vector routing? So distance vector routing operates by each router that maintain a table. That table we call it as a vector. We'll see that why we call it as a vector. Giving the base known distance to each destination and which link to use to get it. Okay. So this distance vector routing actually uses a distributed version of the Bellman-Ford algorithm for shortest path. I think as I was mentioning that in your algorithm course or in the graph theory course, you have already learned about this Bellman-Ford algorithm for the shortest path. So we are going to use a distributed version of it in the distance vector routing algorithm. So the corresponding routing protocol that uses distance vector routing idea is called the routing information protocol, or the RIP. So RIP was the original ARPANET routing algorithm. Okay, so I guess that you know about ARPANET. RSC must have talked it when talking about the history of the internet. So the entire internet architecture came from this ARPANET architecture, and the RIP was the original ARPANET routing protocol. Okay, but still we use RIP in many autonomous systems. It is still a popular protocol. So that remember that distance vector routing is the routing idea, and the corresponding protocol that actually defines that how to implement the idea of distance vector routing, that is the routing information protocol, or RIP. Okay. Now let me explain distance vector routing from the algorithmic perspective or from the implementation perspective. So the distance vector routing, as I was mentioning, that it is a distributed version of the Bellman-Ford algorithm, and I guess that you already know the dynamic programming equation of Bellman-Ford, that is dxy. Say dxy is the cost of or dxy is the cost of the least cost path from node x to node y, and cxv is the cost from node x to node v, where node v is the set of neighbors of node x. Okay, so then dxy equal to minimum of c of xv plus dv of y. So what does it indicate? It basically indicates that to find out the shortest path from X to Y, you look into the neighbors of X. Okay, you find out that you take the cost for the link between X and V. With that, you add the shortest path distance between V and Y, and the minimum of all these combinations is your shortest path from X to Y. Right? So that you have learned in your algorithmic course, and you have used the dynamic programming based approach to solve this Bellman-Ford algorithm to find out the shortest path. Well, but in case of my implementation of distance vector routing over the internet, we use a different approach from the approach that you have applied in your algorithmic course. So in your algorithmic course, what you have done? In your algorithmic course, you have taken the source, you have find out, okay, so what is the cost for all the nodes, okay, and then accordingly you have taken, say if X to Y, say if V1 is an intermediate node between X to Y, then you and X to V cost is known, and based on this dynamic programming, you have find out the cost from V to Y, and accordingly you have found out Dx to Y. Okay, you have started from source and recursively computed the path. But here we will do the reverse in case of internet. Okay, we'll start from the same, that means the destination, and we'll recursively construct the shortest path from all the nodes in the subnet. Okay, so based on that sync tree idea, and that is the modification we are doing here while implementing the distributed version of the Bellman-Ford algorithm. And we will see that why we are doing it from the sync. Actually, from the sync, it gives us more robust way to optimize the path calculation algorithm. Okay, so typically in your standard algorithmic dynamic programming approach, you start from source, but here we are starting from sync. Well, so let me explain it with the help of an example. Well, so I hope that the slides is visible to you, which shows the diagram and the corresponding parts. Okay. So here is first let us see that how the Bellman-Ford algorithm will work in a centralized network. Okay. So in the centralized network, say S is the node. Okay. So I want to find out the shortest path from all node towards S. Well, so how will I do it? So I will start from S. I will see that A and B has direct connection. So in the I will initialize as S cost as 0, S to A cost is 8, S to B cost is 20. And to reach A and B, my node will be S. And the rest is infinite because I have not visited them yet. Okay. And the second iteration, what I am going to do, I am going to find out what are the nodes that are reachable from A to B and iteratively trying to find out their cost. Okay. Now for S to A, I see it is 8, S to B it remains 20. Now for S to C, I see that I have two parts. I can go via A, I can go via B. If I go via A, my total cost will be 8 plus 6, that is 14. If I go via B, my total cost will be 20 plus 3, that is 23. So my minimum cost is via A. So via A, I will take C as 14. Well, now for D, I see that B is reachable from B. So I take it 20 plus 1, 21. Okay, and I reach D via B. For E, I see I can reach E via B. So for that, my cost is 20 plus 2 equal to 22, and my next hop is B. Okay. Now, in the next iteration, what I am going to do, I am going to do further optimization. Okay. For D, I see that I can reach it via B and via E. Via E, I will have the more cost, so I remain via B. For E, I see that I can reach via C, I can reach via B. If I reach via C, I have a total cost of For C, I had a cost of 14, now 14 plus 1, 15. So I can reach in a minimum cost. So if I reach as C, so I update this as 15. Okay. Now in the next iteration, I see that for D, I can reach via E. If I reach via E, from E to D, the cost is 2. I can add 2 with E, so I will get 17 and I can reach via E. Okay. Then in the next iteration, I see that the thing does not get changed, and after 4 iteration, my system gets converged, and I get the shortest paths. Okay, from every node to S. Now here comes the things. Well, whenever I am going to implement over internet. Well, so these are the points that we need to keep in mind, that how do we move from one iteration to the next iteration for Bellman-Ford algorithm. Okay, so what we are doing here, whenever we are doing a centralized computation of the Bellman-Ford, I am actually looking that what is the currently computed cost for every individual node and whether I have a scope to improve it from there. So for example, whenever we are moving from iteration 3 to iteration 4, I have seen that in iteration iteration 3, E has computed the shortest path from C via 15, and from E, D has a path of 2, so I can use the information from E to compute the shortest path of D. Okay, so that information is actually used in case of the distributed version of the Bellman-Ford algorithm. So we need the currently computed distance information from each node to others in the network, and this information, that the currently computed distance information from each node to others in the network, that is called the distance vector. Now these distance vectors are used to find out the routes between any two nodes. Okay. So in case of routing information protocol, that is the practical implementation of the distance vector routing. The routing table along with the metric field. So if you remember that in the last class I have printed the routing table of my machine and I have shown you how the routing table looks like, and there you have seen a metric field. That metric field is used here. That denotes the cost that is used as the distance vector in case of distance vector routing. Now here comes the example of how distance vector routing is computed in the internet. Okay, so S has its okay. So can you see slide 17?
Yes, sir.
Okay. So S has its own distance vector. So S distance vector looks like this. That is the currently computed information, that S to S, you have a part cost of 0. There is no S to A, part cost is 8. Next hop is 8. S to B, part cost is 20. Next hop is B. S to C, part cost is 23. Next hop is B. S to D, part cost is 21. Next hop is B. S to E, part cost is 15. Next hop is A. Now you receive the distance vector from A. Say S has received the distance vector from A, which says that A to S, it is part cost is 8 and the next hop is S. A to A it is 0. A to B it is 9 and the next hop is C. A to C it is 6 and the next hop is C. A to D it is 9 and the next hop is C. A to E it is 7 and the next hop is C. Now whenever S is computed, S computes its update its distance vector based on its previous distance vector that was there by combining it with the distance vector information received from A. So how it S updates? So S to A there is no change. For S to B, what it observes that, well, S to A the path was 8, okay, and A is announcing that it has a path to B with a cost of 9. Well, so if you add up 8 plus 9, it is becoming 17, which is less than my current path cost 20. So what S can do, S can update its paths to B as path cost as 17 and the next hop as A. Because if it's go via A announces that A has a path with a lower cost, so you can use that to reduce your cost. Similarly for C, okay? For C, the earlier was 23. Now, if A announces that A has a path to C with a cost of 6, okay? Now, S observes that S had a path to A with a cost of 8. So 8 plus 6 equal to 14, which is less than 23. So you can update your cost as 14 by choosing A as the next one. Similarly for D, it was 9 plus 18, 17, which is less than 21. You take it as A. For E, it is 8 plus 7, 15. Anyway, it was 15. So it is remaining as that. So that way, every node, whenever it is getting the distance vector information from other node, based on the announced information by other node, it updates its own information. Okay. So that way, the distributed version of the Bellman-Ford algorithm runs. So if you look into the deviation that we are making from the centralized version of the distance vector algorithm to the distributed version of the distance vector algorithm, in case of centralized version of the distance vector algorithm, S was computing its own information. So the earlier case, S was computing its every information at every iteration, and based on its own information that it has updated, it was moving to the next iteration. Okay, so S was independently computing its iteration based on the assumption that it has the information of the entire graph. But whenever we are doing the distributed version of the Bellman-Ford algorithm, in case of the distributed version of the Bellman-Ford algorithm, the major challenge is that I do not have that entire information, so I have to rely on the information that I am receiving from others. Okay, that way S. So remember, S is blind. So in case of centralized algorithm, S had that entire information of A, B, C, D. The entire graph was known, but here the entire graph is not known. S can understand only the part that it receives from other node. So when A was broadcasting its own distance vector information, that distance vector information reaches to S, and as it reaches to S, A can find out that well, this is the updated information, and accordingly, S takes its updated decision. Okay. Now, if I compare between the centralized version of the Bellman-Ford algorithm versus the distributed version of the Bellman-Ford algorithm, that in case of centralized version of the Bellman-Ford, both in the centralized version of the Bellman-Ford and the distributed version of the Bellman-Ford algorithm, we are destination oriented. So we are finding out the paths towards C. But in case of centralized Bellman-Ford algorithm, we find out the shortest path from all other nodes to C. Okay. But in case of distance vector routing protocol, we are just doing the reverse. We are finding out the shortest path from the current node to all other nodes that can work as the same. Okay. So are you been able to observe this difference that I was mentioning? So in case of centralized version, AS is computing the shortest path for all the nodes towards this. Okay, so for every iteration we are doing that. But here what we are doing in case of distributed version of the distance vector, distributed version of the Bellman-Ford algorithm, that is the distance vector routing protocol, we are computing the shortest path from each node towards S. Okay, that's the reverse thing. Okay, if you are not been able to understand, let me know. Okay, but that is the very interesting and the crucial part, well, where we are moving from your algorithm that you have studied in your algorithm class, and the way we are actually implementing over a network. Well, so in your algorithm class, when a node is given, what you have done that you have found out the shortest path from that node to all other nodes. Here what we are doing, we are finding out the shortest path from all other nodes to this node. Okay. So why you are doing this? Any idea? Just think of it. Why you are doing this reverse thing? Okay. Try to think of an left node answer, or otherwise, if you are not been able to understand this difference between the centralized version of the Bell-Manford and the distance sector routing or the distributed version of the Bell-Manford, also let me know. I will be happy to repeat it. Any idea, anything is coming to your mind why we are doing it like this way? Why we are making these changes in the algorithm? So in case of centralized version, I was basically observing, or Tess was observing, that what is its current update. Then based on the available information from the network graph, it was finding out whether it can find out a more optimal path towards another node. But in case of distributed version of the Bell-Manford algorithm, the distance vector routing algorithm, what we are doing, we are taking the information from A. A has already found out that it has a shortest path to C, and we are taking that information to find out that, well, if A can use that path, shortest path to reach to C, and I can have a low cost to A, and the summation of that is lower to my current path towards that node, then I will go higher. Okay, I will update my information. So the reason is because of something like this. Think of the convergence criteria of both the algorithms. Okay. So in case of a centralized Bell-Manford algorithm, you actually know the number of iterations required. Okay. So for n number of nodes, you need n-1 iterations. Well, so whenever you know that how many number of iterations you need, you can do a synchronous update of the distance table. Okay, because you have the entire network graph available. When the entire network graph is available, you can just simply take the current information, and based on the current information, you can update to find out the next one. But in case of distance vector routing or the distributed version of the Bell-Manford algorithm that we are thinking here, you actually do not know how many number of iterations are required. Well, because you do not know how many number of nodes you have in the network. And the number of nodes in the network may change dynamically. You can switch on a new machine, or you can switch off a new machine. Okay, so that kind of changes you can do. And that is the reason that you cannot do synchronous update of the distance table. Well, what is meant by synchronous update? The synchronous update means that the entire network, the information of the entire network is updated simultaneously. That is not happening here. Every node is working individually and independently. Whenever I am getting certain information from one node, I am updating my local information. Okay. So it is something like that. I have my neighbors. Whenever my neighbors have done certain update, I have got that information through some broadcast message, and I am updating my own information. Okay. In a similar way, say my another of my neighbor that may update their information at that instance of time. Well, and all these nodes are working independently, and that way they are asynchronous. And because this is asynchronous, or the distance vector updates are asynchronous, you really do not know that after how many number of iterations you need to stop. Okay. So that way, because you do not have any kind of fixed convergence criteria, the best thing that you can do is like you update your local routing table asynchronously as and when you receive an update from a neighbor. So whenever your neighbor is forwarding an update, you just do a recalculation and check whether you can update your local routing table or not. If you can update your local routing table, you update it and rebroadcast it to your neighbors. Okay, and that way your neighbors will get the updated information. So that way the things will go on forever. So it is not like that in case of centralized Bellman fault algorithm, we know that after n-1 iterations, you need to converge, so you stop after n-1 iterations. But in case of distance vector routing, we do not have any such kind of fixed convergence criteria. Whenever I am getting certain information from my neighbors, I will update my local routing table. And that is the reason we have made this change. Well, we cannot do synchronous update, but if I just try to find out the shortest path from every other nodes to myself, I need this kind of synchronous update. I need the information about the entire network. Well, without that, I cannot do. But if I want to find out that, well, what is the shortest path or what is the optimal path to reach one particular node, well, just do the reverse stream, and that way, one of my neighbor announces that, hey, I have a shortest path to B, well, and this is my shortest path to B, and I find out that, well, if I map my neighbor's cost with the shortest path that is announced by my neighbor, the total path cost becomes less than what I had computed earlier. I can update my local routing table asynchronously based on this updated information. Okay, so that way we will make such kind of algorithmic change when practically implementing the Bellman-Ford algorithm in a context of internet routing. Yes, any idea or any doubt up to this point? Anything is coming to your mind? And this is actually a very interesting engineering example that was applied over the internet, and that is the task we the network engineer does. Well, we take the basic algorithms and we see that if we try to implement that algorithm from an internet perspective, what is the challenge that we are getting? Right? And accordingly, we try to update the challenges or update the solution. Right? Many of the time, I think in the context of TCP, you have seen that we do different kind of jugaad. Okay, so no one knows that why the TCP designers, they have taken certain values for computing this average RTP. The Jacobson's equation that you have learned in the context of TCP. Certain numbers have been taken that, and that is something like a jugaad. Well, so similar thing we do in every cases of system engineering. We take the basic algorithm, we try to preserve its properties, but based on the practical need, well, we do such kind of changes in the algorithm. Right? So this distributed version of the distance vector routing, that is the distributed version of the Bellman-Ford algorithm, might not be computationally efficient, but indeed it is not computationally as efficient as the centralized version of the Bellman-Ford algorithm. But the thing is that it is more practical from the implementation perspective on a real network. Okay. So if you have any doubt, let me know. Okay.
So within an AS, there might be millions of nodes. So each router has to maintain a vector of that big and broadcast it every time there is an update.
Good question. It is not actually the million of nodes. So you see that this set of routing protocols that we are talking about is the intra-autonomous system routing protocol or the routing protocols within an autonomous system. Right? Now, within an autonomous system, we do not have that many number of nodes, typically. And later on, maybe in the tomorrow's class, we are going to discuss that typically we have a bound on the number of nodes that we typically keep within an autonomous system. Right? But within an autonomous system, if you have 100 different nodes, then your distance vector size will increase in that order. Right? And that is actually one of the reasons that we do not apply such kind of IP-based routing algorithm. So IP-based routing algorithm, one algorithm is this distance vector routing algorithm. Another algorithm we'll see tomorrow, that is the link state routing algorithm. So both the algorithms have such kind of limitations that if you want to implement it internet-wide, you will see that they will never be able to converge, and you need a huge amount of information, and collecting that information itself is, you cannot visualize. prepare. Well, so that's why we implement all these algorithms within an autonomous system. That I want to forward a packet from one node of the autonomous system to another node of the autonomous system. We apply such kind of algorithm. But to forward the packets from one autonomous system to the next autonomous system, we'll see later on, maybe in the next week, that we use a complete different kind of idea where we do not try to optimize the cost or something like that. Okay, there we are more concerned about finding out a path rather than optimizing the cost of the path. Because in that large scale, you cannot optimize the cost of the path. Well, and this is actually an important aspect that you have raised. So in internet, we always have this kind of trade-off between the performance and the correctness. Right? So if you want to, if you are planning to take computer network as your future career, if you want to join to a company like Cisco, Netgear, that kind of company, or you want to take up computer network as your future research agenda, always keep in your mind that you will never be able to optimize both performance as well as this correctness together. If you want to make the protocol correct, you will see that the performance is horrible. You cannot actually implement it in a practical network. So that way, to improve the performance, you need to do some kind of jugaad that will possibly violate the protocol from the correctness, but it will work over internet. And that kind of things we do in this hierarchical way. That within autonomous system, we try to make it, or to try to use the protocol, we will find out the shortest path. But here you have seen that you cannot scale it up. To scale it up, you need large number of nodes. So that's why within the autonomous systems, whenever we talk about the BGP protocol, you will see that here we are only concerned about finding out a path. Or we use something called a reachability information. We just try to find out that whether this particular autonomous system is reachable or not. That's all. I never try to find out whether that is the shortest path or that is the longest path. If it is reachable, I am happy. But within autonomous system, I will try to optimize, or I will try to find out a kind of optimal path at the best which is possible. Any other doubt? Okay, then let me stop here today. Tomorrow we'll carry out this discussion of distance vector routing protocol. We'll see certain issues in the distance vector routing protocol, and we'll move towards the next routing protocol that is also used in the internet, that is called the least state routing protocol. Okay. Okay. Thank you all. That's all for today. We'll see you tomorrow morning. Then take care. Bye bye.